In this video, we're going to be doing some sample problems related to strong acid and strong base calculations. There is a big difference between strong acid and strong base calculations versus weak acid, weak base calculations. In the previous video, we saw some important relationships between hydroxide, hydronium, and different formulas. And so we're just basically going to be applying those relationships to strong acids and strong bases. So let's start with the first example. A sample of tap water has a measured pH value of 6.8. What is its pOH? So we learned the relationship that pH plus pOH is equal to 14. And by the way, you can try these questions on your own because you know the relationship. See if you can apply them and check your work. So you pause the video, try it, and check your work. So we know that the pOH is going to be equal to 14 minus the pH, which is 14 minus the 6.8 value there, and that should give you 7.2. Try to keep the same number of sig figs. This is the pOH value, and this would make sense because the higher the pOH, the less basic. This is an acidic solution. pOH is sort of like the opposite scale. If you're above 7 in pOH, you're acidic. If you're below 7, you're basic. And here, if pH, you're below 7, you're acidic. So this is consistent. All right, next question. We're going to learn a bit of a concept here. If 0.02 moles of HBr gas is dissolved in 1 liter of water, what are the concentrations of the hydronium and hydroxide ions? Determine the pH. So first of all, you need to understand this is a strong acid. That's actually a very important component of this question. We're dissolving that strong acid in water. So the concentration of the strong acid is going to be HBr. Once dissolved in water, I know it says gas here, but when you dissolve it in water, it becomes aqueous. Is going to be 0.02 moles divided by 1 liter, 0.02 molar. Now, because this is a strong acid, we know that when you put it in water, it's going to ionize. You're going to make it react with water, and it's a one-way arrow because it's a strong acid, and you're going to get Br minus aqueous plus H3O plus aqueous. Now, because it is a strong acid, if it ionizes, 100% of it is going to become this stuff here. So that means that if you know the concentration of the acid itself, which is 0.020 or 2 molar, then that's also the concentration of the H3O plus, because all of it is converted into H3O plus. It's a 1-to-1 ratio. If it was 1 to 2, you'd multiply by 2. But you simply know that the H3O plus concentration is the concentration of the acid because the ionization happens at 100%. So now that we have the concentration of the H3O plus, we can find the, let's write this down here, concentration of H3O plus is equal to 0.02 molar. We have to find the concentration of OH minus. We know that Kw is equal to concentration of H plus, which is H3O plus, times OH minus. So if we want to find OH minus, we just do OH minus is equal to the Kw divided by concentration of H plus. So that means that we have 1.0 times 10 to the negative 14, it's Kw, divided by this 0.02 molar here. And so it's going to give us, let's do that, so 10 to the negative 14 divided by 0.02 molar, we get 5 times 10 to the power of negative 13 molar. And that would be the concentration of OH minus. There are many ways you could have done this. You could have also calculated the pH first and then found the pOH and then converted the pOH to the concentration of OH minus. Our last step is to find the pH. Remember that pH is, I'll do the work here and I'll put the final answer to the side. pH is negative log that's negative there, of H plus. So that's going to be equal to negative log of 0.02, which is, so let's do the log of 0.02, and we get about 1.69, or keeping it to 2 sig figs, 2. So the pH is 2. And this makes sense. The H3O plus concentration is higher than the OH minus concentration. This means the solution would be acidic, and a pH of 2, which is less than 7, supports an acidic pH. So in this question we learned that if you have the concentration of an acid, the concentration of the H2O plus is simply that concentration of the acid, because all of the acid ionizes to H3O plus in solution, providing that it's a strong acid. This would not work for a weak acid. You'd need something a little bit different here. All right, we're going to go ahead and try a similar approach with a strong base. So what is the concentration of hydronium and hydroxide ions in a 0.0030 mole per liter solution of magnesium hydroxide? Determine the pOH and the pH. So, as we know, the magnesium hydroxide is a strong base. And so when you put it in solution, it is converted to magnesium 2 plus OH minus AQ. Now in theory, this is really just a solubility. It is an equilibrium, but it's a strong base, and the equilibrium lies so much to the right side, it really is one way. So that's actually going to be very important here. Let's balance this, get a 2 here. So all of this is converted into this stuff here. So that means if you know the concentration of this, you can find the concentration of this over here by simply using the ratios. There's no need to write KSPs or Kas, KBs, because that's only for weaker stuff. So we know that the concentration over here is 0.0030 molar, which means our concentration of OH is 2 times that, because it's a 1 to 2 ratio. So 2 times 0.003 molar, 0.0060 molar would be our concentration of OH minus. So we found that, and the reason we're finding the concentration of OH minus is because we want to find the pOH and the pH. So now that I know the OH minus, I can just do pOH is negative log of concentration of OH minus, which is negative log of 0.0060. So let's do that. So log of 0.0060, and I get about 2.22 or 2.2. And then for the pH, I can simply do 14 minus pOH, which is 14 minus 2.2, and I get about 11.8. And I do want to keep only 2 sig figs, so I would have to round this in this situation to 12. Now keep in mind, when you do add the pH and the pOH together, it should add up to 14, but rounding changes that a bit. Just keep that in mind. So I always like to keep my pre-rounded numbers just to make sure it adds up to 14, then I round afterwards. All right, so that was a question where we had a strong base, and what's important is that you understand that was a strong base. So even though we wrote this as an equilibrium here because of KSP values and stuff like that, in reality, all that's happening is that it's a strong base, so all of it's ionizing 100% to become the magnesium and the OH. And so when you have a strong base, if you have the concentration of that base, it's simply the concentration of the OH as well, multiplied by that coefficient. Sometimes it's 1 to 1, sometimes it's 1 to 2, 1 to 3. It depends on what you have there. But that's why it's important to memorize your strong bases and your weak acids and your strong base acids, because that will affect the way you approach these calculations. Okay, so the concentration of nitric acid solution is 3.6 times 10 to the negative 4 moles per liter. Determine the pH and the pOH. So you can try these on your own now at this point. So here, notice we do have a strong acid. So what that means is that when this acid is put into water, it's going to ionize 100%, so to completion. We're going to get some nitrate, NO3 minus AQ, but then also some H3O plus, or H plus, we can call it AQ. And it's 100% because it's a strong acid. So we know the concentration over here is 3.6 times 10 to the negative 4 molar. It is a 1-to-1 ratio because there's only one H here. And so that would be also 3.6 times 10 to the negative 4 molar of H3O plus. So now that we have that concentration, we can find the pH by doing negative log of the H3O plus. I'm just going to write it as H plus to keep it short. So log of the 3.6 times 10 to the negative 4. And you get about, I'm just going to round for my answer here, but I'm going to keep all numbers in my calculator, 3.4. And then for the pOH, once again, we're going to do the 14 minus pH, which is 14 minus 3.4. And we get about 10.6, or approximately 11, if you're rounding. Again, that was because we had a strong acid. We could assume that the concentration of the acid basically gives us the concentration of the H3O plus. And now that we have that, we can do the negative log of H3O plus to find the pH, and then from there you can find the pOH. All right, so let's take a look at the next question. Again, you can try it on your own, and then check your work. Determine the concentration of hydronium and hydroxide ions if the pH of a solution is 4.2. So we know that if you want to find the concentration of H3O plus, you can do 10 to the negative pH. So that would be equal to 10 to the negative 4.2 molar. If you evaluate that in your calculator, 10 to the negative 4.2, you'll get about 6.3 times 10 to the power of negative 5 molar. Now, once you have the H3O plus, you could find the OH by doing your other relationship, which is the Kw over the concentration of H plus. So that's going to be 1.0 times 10 to the negative 14 over this concentration here, 6.3 times 10 to the negative 5. So let's do 1 times 10 to the negative 14 divided by that answer, and you get about 1.6 times 10 to the negative 10. 1.6 times 10 to the negative 10. And so this is our concentration, so it's molar. And I just want to double check that to make sure it worked out. So we have 10 to the power of negative 4.2. So we have 6.3 times 10 to the power of negative 5. That's good. Then I'm going to do 1 times 10 to the power of negative 14. And I'll divide it by the answer to get 1.6 times 10 to the power of negative 10. And if you multiplied that back with your 6.3 times 10 to the power of negative 5, you would get very close to the 1.0 times 10 to the negative 14. So now here we have our last question. Our last question here is, what is the pH of a 0.64 molar solution of HClO? Explain why this problem cannot be solved as simply as the ones above. So think about this carefully. A lot of you right now might be doing this. You might be thinking, okay, this is an acid. You have 0.64 molar. It's going to react with water. And you're going to get ClO minus AQ plus H3O plus. And so you might be thinking that, okay, well, since it's an acid, well, the concentration here must be 0.64 molar. but you must always think about what type of acid you have. This is not one of the acids you were told to memorize, one of the strong acids. This is actually a weak acid. So this one-way arrow does not work. It's actually a two-way arrow. And so we don't know how much of this acid here becomes this. We don't know that. We know it's not 100%. So it's definitely not this 0.64 molar that's your concentration of H3O+. So to do this, we're going to have to employ a different technique. And that different technique is likely going to involve ice tables, Kas, and Kbs. And that's part of the next lesson, which is calculations involving weak acids and weak bases.